Um, okay, welcome everybody. Today we are at week 5. Now, I have the last week's codes open. If you remember, we tried to use a system GS, and we tried to design a PI controller. And while we were trying to design a controller, we've seen that we have a parameter that we should decide on, and we were giving it a random value, and we looked at different designs here. Now, if I run it, hopefully I will get the result here. It takes quite time. I guess we did change some stuff here. Let us quickly look at the problem here that we've defined. Where was it? Here we have the problem here, and we try to solve it. Now let's look at our problem. Okay. Let's say problem here and run it again. Okay. We are not able to define it because we have some size issues here. One starts with s cubed, and I assume that the other one is just s squared. So I obviously have changed something around. Now we can see that our PDS is a sign order, where we have the denominator, where we have the controller. Since the PI controller is adding a degree to the system, to the original system, which was a second order system, we have a third order system. In this case, and if you remember, we were using the dominant pole placement approach, which means that if we have higher order systems, an order higher than 2, then we are not able to calculate the settling time, overshoot values, etc. But what we can do is we can just choose a pole pair which represents a second order system, or the second order part of the system. And if we somehow can design and assign the poles so that these two pole pairs are the dominant ones and the other ones are not that relevant, they do not contribute to the output, then it is possible to predict what the settling time, overshoot, rise time, delay time properties, or the time domain properties, in other words, are. So basically, what we are trying to say is that we have too many poles, but we are choosing only 2 of them, and if they are slow enough, which means that they are dominant, then we can adjust the closed loop time domain properties. Now, in order to be able to do that, we have to choose a PDS, which is a second order system and the dominant pole, and we should add another pole that will be the residue, or the not so important poles, let's call it that. Now, for example, I have a 1 degree gap here. I need to add just 1 pole because the closed loop, resulting closed loop system is a third order system, and I have a second order system. This means that I have to add just 1 more pole. So maybe defining this as a symbol P which represents the pole that should be far away from the dominant pole pair, and then I have to multiply this. So this is the basic idea. If I had a second order system that I was able to design, because I would have had the same amount of coefficients on both sides. But since I have a higher order system and a second order polynomial is not sufficient, I have to add another polynomial which will compensate for the fact that we have a gap in the degrees. Now the amount of coefficients are the same, so I should be able to see what the problem will look like. Now, as you can see, now I have a defined problem here, which doesn't look that much appealing. I might want to go ahead and see what the problem is. Therefore, I need to use this here. I can use the problem length here, and I can just go ahead and display maybe VPA in order to have a nice numerical representation. I can see that there is a fraction which doesn't look that appealing. So if I do this, I should be able to see, or the ith element basically, I should be able to see what my problem looks like, and this is much more better. Now I can see that the highest order terms are equal to each other, which is a prerequisite at this point, since I have to be able to equate them, and most of the time my highest order will not be affected by that. And the reason for that is I am defining my system, my dominant poles with s square, and if I'm adding a pole, I'm just keeping the highest order coefficient 1. And if I multiply them, I will always have the highest order term with coefficient 1. So if the system doesn't result in that, I should then add another coefficient here in order to have a there. I can show that just here if I add p and a, and if I do that, I can see that my value a should be 1. But in case of different gains, I might be compensate for the fact that I don't have the highest order term coefficient 1. Or another possibility is to normalize my closed loop system polynomial, which can be a better option for some cases. It might be not for other cases. Now, how can I do that? Well, I can see that this is my closed loop coefficient list. Maybe I can say coefs then something like that and equate this here, and then I can just say that coefs then is equal to coefs then divided by coefs then first term, which is the highest order term here. In this case, I will then equate this instead of this here. Let me just put it in there. So if I do this, I don't have any a, so I should remove this. If I run this, I can see now this doesn't change much, but if I had a different value on the left-hand side, since my control parameters are here, I can assume that this is the left-hand side, which represents the closed loop transfer function characteristic polynomial. If I had, let's say, 14 as a coefficient here, it would have been normalized with this code. So there are two approaches to that. Choose whichever is better in your opinion. I guess I didn't plug this in here. So this is what I mean by that. And this won't change anything since it is already one, but in other cases it will be helpful and useful. Now I will go ahead and get rid of this and basically use this and semicolons to one. It's not necessary there. Okay. Now I can see also that I can count how many non-trivial equations I have and how many unknowns there are, so I can determine what my solution will look like. Now I have p, I have omega n, I have KP and KI. So basically, I have 4 unknowns, if I'm counting right, and I have 3 non-trivial equations because this equation doesn't contribute to the problem. It's just a non-trivial one, and if I go use simplify on the problem here, I will see that this will be converted into a true statement. You can see that this is just 1, which means true, and it doesn't mean anything for me. So I have 3 basically equations and 4 unknowns, which gives me infinite amount of possibilities to choose P, omega, and Kp and Ki pairs here. So it's a 4 degree equation set, and I have a relation between them and 1 free parameter. I can choose the free parameter as I wish because I can go ahead maybe choose P, then I can evaluate omega n in terms of P and use omega n and P here in order to evaluate the Kp in terms of P, and then it's also possible to look for Ki. Now I can go ahead and tell Matlab to solve for Ki, Kp, and possibly omega n, and it will look for the left parameter here, which is P. I didn't mention P, so it will use P as a parameter, as a free parameter, and it will represent the solution if it's possible to solve this equation set. And if I look at the solution, I can see I have a solution, and if I say sol.kp, I will have something like this, which isn't readable at the moment, but if I use VPA and do this, I can see that I can calculate the Kp parameter if I know or if I plug in a value for P. It is also possible to look for the other ones, Ki and even omega n, and I can see that everything is in terms of P. Maybe I should plug in P greater than 4 or P can be equal to 4, then this will be 0. So if P is equal to 4, then Ki will be 0. If Ki is 0, then this controller becomes a P-type controller. So keep that in mind, and if you don't provide this and try to solve this, Matlab will try to give you a solution, but it might be a trivial solution, and most of the time it is basically. And you can see that sol.ki, if I'm not wrong, is equal to 0. Is it exactly? And let's look at the solution where what the p-value is. You can basically see that it is 4. Since choosing 4 will reduce the freedom, it will somehow project to the three-dimension solution set from the 4-dimension. So it will give you a random or a solution that exists but isn't that important for us. So if you accidentally go ahead and solve and see this is my solution, you should always go ahead and check your controller, because it might be a different controller than you expect. You start with a PI controller and then you might end up with a P-type controller. It depends on the parameters. And you can also end up with a I controller which doesn't have a Kp parameter or is set to 0. Then you have a different controller. But keep in mind that all P-type controllers are a subset of PI controllers, because it is a special version where Ki is 0. So if you think of that way, it is a subset of the possible solutions. But if we insist on having PI controllers, this means that at least you should have a Kp and Ki parameters, since a PI controller consists of P and I parts. You might end up with I-type controller, that might be the case, but if you end up with a P-type controller, it is also possible, but you are basically not placing an S to the origin, or you don't have any integrator. And there are some possibilities. You might be not needing a PI type controller for your problem, or you might be in wrong places, or you did something wrong, so you end up with a different controller. So it depends on the system, it depends on the setup, so you should be aware of what you're doing. That's the important part here. But let's move on. I said that I can maybe choose P different. If I want to do that, I have to provide here which parameters will be solved in terms of the left free parameters. So I should provide this here. I can also change my mind and say, okay, maybe I want to solve P, and this can be more sensible for the fact that I can choose P such that it is a positive number. In that case, I can assure that the whole closed loop system will be stable, since S plus P has the solution S equals minus P, negative P. So if this is the case, I can see that if P will be positive, I will be always on the left-hand side or in the S domain. So this will be always adding a stable pole to the dominant pole pair. Since I'm choosing the dominant pole pair with zeta and TS, I most probably will choose theta greater than 0, which means that I will most probably choose my pole pair in the stable domain or on the left-hand side on the S domain. So if I'm knowing what I'm doing, if I'm aware of what I'm trying to do, then this parameter P and searching for the parameter P and using the parameters or the free variables here is a better idea in my opinion. So let's try that and see if we can end up with a nice representation that can us show what the condition for stability will be. Since if you think about it, if I have a third order polynomial, determining the stability needs the root-Hurwitz criterion or some other stability checking algorithm. But in this case, since I have assured that the two of the dominant poles will be on the left-hand side, I'm just looking at the third pole, and by checking if it's a positive or negative value, I can determine the stability. This is much easier than going and looking for a stability test. So keep that in mind. Now let's look what the solution looks like in terms of P with a parameter, and I can obviously see that if I want to choose a stable solution, then I can solve this omega n value. I should divide 4 and this value here. So having a greater value than 3.38 should give me stable solutions. Now also keep in mind that I want to maybe maximize this parametric function, since I want to have a dominant pole pair, and this pole that I'm examining now, or the value of P, should be as big as possible, since it will be further away on the S domain. So it makes sense that I want to maximize this. So if I have, let's say, omega n 0, it should be 4. If I have 1, it should be, I guess this is equal to omega n 1. Oh, no, I'm sorry, this is equal to omega 3.38. I might choose omega n 1, which will give me a good solution here. So let's try to, let's first of all see this, and maybe I want to, I can convert it into double. Let me subs into this solve P. I don't need this. I can go ahead and choose a value for omega n. Let's say 0.1, or let's say 1. Now, if I look at this, I can see that I have 2.8177. Let's choose a different value for omega n. Let's make it bigger. I can see that it will become less, and if and since I'm calculating the p-value here, so this will be at minus 1.63. this will be at minus 2.81. So having a lesser omega n value will be better. So omega n can be 0.1 here. This could be a good idea. And you can see that it becomes 3.88. So it will be on the left hand side, and it will be at minus 3.88. But keep in mind that this omega n is also a parameter that affects the dominant poles. So my dominant poles will become slower since I have a certain zeta value, but I have a less omega n value. And if you remember the settling time formula, it was something like this: zeta times omega n. If you fix zeta and plug it in, you will see that this relates. This relation is an inverse relation. If I'm decreasing the value of omega n, Ts will be increased, so the settling time will be a bigger value, which means that the system will become slower. So the bigger the omega n, the slower the system. That's basically the relation. So I'm sacrificing speed for the dominance here of the poles. Let me just go ahead and maybe solve this by choosing omega n 0.1, and I might also go ahead and choose it a different value and compare what the result will look like. So let's say kp1 here should be double, and I should substitute sol.kp. I'm changing the omega n value, and I decided that it should be 0.1. And if I have the ki value, I'm going to choose ki and give it a different value. Now I will define my system here. I guess it is not necessary to try these here. I will just calculate the closed loop system by using these values, and since I have defined them differently, by the way, I somehow turned the PID design problem into a PI controller design, and I was talking about this in the last lesson, so that was why I ran the program and got an error. Now, since my controller term is kp times s plus ki divided by s, I will first give kp and then ki. So this way I will define it. Since I have an integrator, I should also change this here. Now I have the first controller that I've used here. I will also define the second one, and this is not necessary, so I can also use a different solution set here. Maybe, let's say, to a much faster solution, and I will see what the difference will be. Now fs2 will use the second coefficients here, kp2, ki2, fs2. Now we have some stuff here. Let's give it a time vector here, 0.1, let's say 5 seconds, maybe 10 seconds, since I have also a slow solution. I give it the time, I give it 1, and I say this is y1, info 1, this one, and poles 1, ts1. So I will repeat this for the second solution set here. y2 is equal to ts2, and also ts2, ts2, info 2, and poles 2. Now I can also go ahead and did I create a figure? I guess I did. So basically I can use this here and adapt it a little bit. I have info 1, I have y1, and this lower one should be, let's say, black. And I have a display name. This means that the first system is intact. Now I will also plot the second one on top of that with a red color, and I will give it a settling time too, and this. And basically time and yt will be like this. Overshoot values, well, I'm not really interested in that. I might just say that this or maybe let's get rid of omega and then zeta. Instead of the solutions, I might want to, well, I don't need anything here. I decided to just give it a step response comparison. And that's it. And I can show the legend. I don't want to do anything like that. I'm then going to use the pulse 1 here, pulse 1, pulse 1 here, and again with black, and then TS1 and info 1. Maybe I should use the overshoot here. So the one figure will show the settling time, the other one will show the overshoot value. Now I'm changing it to 2, and back to 2, red, info 2, and TS2. And I'll open this. I'm not really interested in this, as I've mentioned. I'm just going to say that this is the pole spread comparison. There we go. Now let's run this, and hopefully, okay, now I can see what's happening here. Now the red one is like that, and this one has a response like that. But you can see what I mean by the dominance here. The factor here is very much, you can see that this is 3.8 and this is 0.1, so 38 times away from the origin, but this is not that much apart from each other. And you can also see that my first system, which is too close to the j omega axis, it has a large settling time, and you can also see how the relation between those settling times are. Now I can now see and assess the situation, and I can say that okay, this was an overkill. Maybe I need to increase my omega n value a little bit. So there should be a trade-off between them. It's not a good idea to overkill. Now let's see what happens. Now I can see that I have a better situation here. Some unwanted things happen. I don't care about that for a moment. I have a better settling time, but still this looks a little bit better since it is not what I want, but it does do the job approximately. Now I don't remember what my overshoot was. It was 10%, and basically this is almost 10%. So my settling time, 3-second settling time, and my approach here is pretty good. I don't say that this isn't 10%, because if I increase the time here, I might see that it also should have the same zeta value or same overshoot characteristics, because I was trying to set the settling time, the overshoot value here, and you can see that it doesn't affect that much. It has the almost the same zeta value. It doesn't have the exact value, because I don't see the effect of the zero at the moment, because I didn't place the zero. I might also want to do that, which will be a good idea, since it is also important where the zero of the controller is. Now, since I have a PI controller, or starting with the PI controller or PD controller, we will add zeros to the system. We are not concerned only with, or we are not just changing the poles or adding poles. We are also somehow adding zeros, which might be a good idea, which might not be a good idea. It depends on the situation. And most of the time, the zeros will change what we are trying to do, because if we just had poles, it would be pretty much easy because just change the pole positions according to your setup and you're good to go. But if you have a 0, as you will see in a moment, then it will mess up your objectives probably. And if you remember, we've seen the effect of the zeros before. If we have a 0 in the dominant region, it is very bad. It's even worse than having a pole at the dominant pole region. It was having a 300% overshoot value, whereas the pole was just 100% overshoot. So keep that in mind. Now I can easily determine where the position of the pole, the 0 is. It's exactly related to this numerator here. Kp1s plus Ki1 gives me the position here. Now I can determine the position of my 0, and since this is Kps plus Ki, the solution is at minus Ki divided by Kp. So minus Ki divided by Kp. Minus Ki1 divided by Kp1. And the imaginary part will be 0 since it's just one 0. Since it's a real value. Now, I will not go into the detail of that. It might also mess up my whole thing. Let's go here. Now, I don't need a display name. I will also change how it looks. It should be a circle. Now let's also plot the second one with a red circle. Now let's repeat it. Now I can see why my effect that I was not very happy about is taking place. Since I have a 0 on the right half plane, I have a unwanted effect here, an undershoot basically. So if I wouldn't have this, if I somehow didn't add this 0, it would have been a better solution. This solution, where the black one, would have been a better choice. But since it's adding its 0 and the 0 is now dominant and has it's even on the right hand side, and keep in mind that this is not a pole, this is a 0. So having a 0 on the right half plane is not that much ideal, but it's not affecting the stability, since the stability is calculated or determined based on the poles of the system, not on the zeros. So the 0 affects the system, but not the stability. But step response or transient response or even the steady state response can be affected by a 0. Now I can also see that my 0 and my pole for the red one are very close to each other. Now just relax and think about what this means. If I had a transfer function that had just this 0 and this pole, what would it look like? And I can also see what the value exactly is. It's let's say it's 1.7. I have a 0 at 1.7 and a pole at 1.69. At minus 1.69. So if this would have been represented with a transfer function, what would be the transfer function? Now obviously, my transfer function would be s plus 1.7, since this is the numerator, divided by s plus 1.69. If they would have been on top of each other, then I would have had a transfer function that would look like 1.7 divided by 1.7. So you can see that this will cancel each other out. And I would have a transfer function that would be equal to 1. which is a dream of a control engineer. Since in the steady state we are trying to have a gain that is 1, if you have a system that doesn't have a transient response, and it's just ideally 1, you will have a perfect closed-loop system that tracks only the input. And this is also the reason why we most of the time have something called system control with its inverse. Now, if you have a system transfer function GS, and if you design a controller that is the inverse of the transfer function, and if you connect them in series or a cascade, you will see that you will get the result 1. Think of this. If I have ds 1 divided by s plus 1, and if I'm designing a controller that is exactly s plus 1, if I'm multiplying them, fs times ds should be equal to 1. And this is open loop. Since I'm just connecting them cascadely and there is no feedback structure, this is open loop. But it is exactly equal to 1. And if I have an input-output relation that is equal to 1, that means that I will instantly, with no time delay, with no other effect, with no transients, I will instantly get the response in the output. So, sometimes you might see some approach that will use this method here to design controllers, but this is not closed loop. So, what does it mean that we don't have a closed loop, and what does it mean that we are using an open loop strategy here? Well, basically, if you remember, I did talk about an example, a room temperature control system. Now, if I'm using a controller that uses the inverse of the system, then I should have the exact model, first of all. The model should be minimum phase, which means that I should have all poles and zeros of GS. All poles and zeros. This was not the case for our closed loop control strategy. All poles and zeros should be on the left-hand side. If not, I have some issues because the inverse will be on the right-hand side. If there's something on the left-hand side. Let's say we have s minus 1 divided by s plus 1 as a system transfer function. Let's say gs is equal to this. The inverse for the controller will be s plus 1 divided by s minus 1. So this isn't a stable controller. And this will cause for internal stability problems. And practically, it's not possible to use this controller because it will become unstable. It will generate a signal in the internals of the closed loop, or even in this connection here, that will get out of control. A signal that is not settling down to a value or is not bounded. An unbounded signal will be generated here, namely the control signal. Now, that's a risk that we will not take in the practical world. Now, if you remember the room temperature control system, you should know the system exactly. The system should be minimum phase, and also there should be no effects that you didn't take into account. By that I mean you shouldn't have a disturbance or noise, since you are not able to reject disturbances if you have an open loop, since you are not looking at the output. What open loop means is that I'm guessing what I should apply to the system by looking at its mathematical representation and taking the inverse. This means that I'm guessing my control input, and I'm not checking the output if it's what I was expecting. If you have a closed loop system and you apply a control signal, you go ahead and look for the error because you are measuring the output and you have provided an input, and you look at the difference and then take action for that. But for an open loop controller, that's not the case. You're just applying a control signal and you're leaving the room, or you're leaving the control system on its own, and you pray to God what happens. Because you're not measuring the output. There's no measurement. So if you're comparing closed loop and open loop, the closed loop system is economically a little bit expensive, since sensors are expensive, but you're restricted on that, because if you want to control and if you want to have a high precision control on the room temperature, of course you have to go ahead and measure the room temperature. You can just design a heater slash cooler that is guessing the room temperature. That's not that ideal, because you do not check the physical quantity there. You have to check the room temperature, and if your reference is different, then you will act on that. You will cool or you will heat the room. And also, if you have a closed loop system, if someone opens a door or someone opens a radiator, if there is a source of heat or something else, you can take action for that too, even if you didn't compensate for that. Your feedback structure will compensate for that, because you have a feedback structure, you have error, and your controller, if you have a stable controller or stable control system, closed loop, then the error should tend to zero at steady state. So if there's something happen, transients happen, then you will tend to zero for the error. And if that's the case, then your reference tracking will be successful. So now, enough talk here. You can now see that the zero and the pole for the setting or where we have red are very close to each other. So this is a pole zero cancellation, and if we have a pole zero cancellation, we will be happy. Especially for high order systems, because the system automatically will decrease in degree, since you are placing the zeros such that your third order system will become a second order system. And we can see that here. Let's say ZPKTS2 here. You can see that I might also approximate this system with another transfer function where I don't include these two pole and zero pair here. This pole and zero pair here. It looks like a system that has a gain omega n square, not exactly, but it's almost there, plus s squared plus 2 omega, 2 zeta omega n s plus omega n squared. So it looks like a second order system, and if it would have been a little bit closer to each other, it would have been a better approximation of a second order system. And the dominant pole placement is a solution, but this reducing degree is a better solution in terms of approximation of the system response. In dominant pole placement, you have fast poles, you have the same degree, but in pole zero cancellation, you are reducing the degree, so it becomes more like a second order system. So that's that. And this is also explaining why this is working better in terms of overshoot, since we said that we will have 10% overshoot, and it has approximately, what is the value here? 9.33% overshoot, which is sufficient in this case. But the other one doesn't have that, and the other one has some adverse effects in it. This is the reason why. Now I can still tune a little bit here. I know that the value of 2, and I don't know what the value I shouldn't pass was. I guess it was 3.88. Let's try 3 here. Let's say this is 2, and let's say this is 3. So the new thing will be the red one. Now you can see that this is still not a good idea, because they separated a little bit and they are on the right of this line here. So this is also not wanted. And you can also see that my 0 is really affecting my system. I don't have the overshoot that is desired here, and I don't have a nice response in terms of transient response. Now think about the response like this. You are sitting in a car and this car is accelerating, and its acceleration profile looks like the step response I'm seeing in figure 1. Now which car would you prefer? You have a car that looks like the black one, and the other car that you experienced looks like the red one. Now, it's not a good idea to have some profile that looks like red, because you're accelerating to a point and then you're decelerating and you're accelerating back again, and it takes too much time to get to that speed. In the case of the black one, you're just, since I have designed it with 10% by the way, you're just getting to the speed limit, or you're accelerating with a little bit higher than expected acceleration, and once you are there, you're just slowly taking or decreasing your acceleration, since this is not speed. Or you can also think this you can also think of this as a speed profile, etc. But the most ideal thing you would want to have is a first-order system response with a reasonable settling time, because it will smoothly increase and stop at the desired value. Overshoot is not that a good idea, and we can also change that here. Since I have calculated zeta, maybe I want to have zeta equals 1, and I'm commenting this out here. Now let's try this, and we did not succeed for the fact that I have something 0 here. The problem is here, so I can see that P and omega n Kp Ki, since it's still the same solution, sol dot Kp, sol dot Ki, sol dot P, and I can see that omega n should be, I guess, less than 2. Where is my, okay, there it is, and you can see I have tried 2 and 3, which makes the system unstable. Let's try 1 and 1.5 to be sure. Here we go, we have this response now. Now this is a different design than what we've started with. They're pretty close to each other. Don't mind that this looks like a pole pair. It's a numerical error since it's 10 to the power of minus a here. This means that this is a calculation error, numerical error, and doesn't have anything to do with a pole pair. It's just zeta equals 1. Now I can see that my pole and 0 are on top of each other, I guess. Kp1, Ki1, you can see that it's exactly s plus 2 here. 0.25 s plus 0.5, and if you take the common factor out, you will see that it will be s plus 2. And then I also have a ZBK, let's say ZBK, TS1. I also have a pole there, and you can see that they are exactly on top of each other, so they will cancel each other out, and I will have a system that has a transfer function equal to 1 divided by s plus 1 square. The square here is indicating that zeta is equal to 1, and omega is also 1. So if I want to have a system that looks like this, this is the ideal setup. You can also see that the red one here is not that far away from being ideal, since it has a nice response. Its omega n value is 1.5, and you have a 1 and 1.8, or you can see that 1.5 and 1.8 are close to each other, and then we have 2 poles on top of each other. These are on the real axis. What I mean by that is I have 2 poles here at minus 1.5, and you can see that it has also a nice response. Since everything is real here, you don't have any overshoot. At this point, most of the solutions will be close to ideal because everything is real and you will never get an overshoot here. And the settling time is not that far away from each other. So that's that. Now, this means that we are trying to design controllers, especially PID type controllers, and these controllers have some parameters and structures. But the thing that we are using is the same in terms of Matlab code and algorithm, because every time we are trying to design a controller out of the PID family, we will look at the degree of the system. We will decide if we can directly assign the poles, if it's a second order system. If it's a first order system, it's also possible to directly choose a pole there, and then some other characteristics maybe can be taken into account. But if we have a high order system, our approach will be to use the dominant pole placement. And during this dominant pole placement, we will have some parameters. It might be possible that we have a solution family that's infinite. It might be that we cannot even design a controller. These possibilities are there, but our approach will be to choose two poles, a pole pair that will be dominant, and the other ones will be placed hopefully far away from these dominant poles. I'm not talking about only the poles. The zeros should be held far away from these dominant pole pairs, because it will affect, and it will much more affect, the system transient response here. So zeros are even more dangerous than you think. There might be possibilities where we have a pole zero cancellation, but not always is this a good idea, since it is a hard restriction on one pole and one zero. So we can debate about this, if a pole zero cancellation is better, or if a dominant pole placement that has a high dominance factor is better. That might depend on the system and setup. But most of the time, the Matlab code for PI, PID, PD, and even more controllers that can be derived from those controllers can be designed with the same PID, same Matlab code with small modifications. Now, I will show you in a moment how I will construct this. Now, you can see that I can design a PID controller via pole zero cancellation. I can design a controller via tabulation. So these two are basically covered, and I will show you in a moment how to do this. I will go through that. There's also a possibility to use a whole different idea, the Ziegler-Nichols tuning method, which is a more of a practical approach here. And I will show you in a minute what I mean by that. There is also something called phase lead controller design. This phase lead controller is just a first order controller, a generalized PI controller in different terms. And the difference here is that you don't restrict your pole to the origin. Now, if you remember what a PI controller looks like, let me just show you in a second here. We know that the PI controller looks like this. KPS plus KI divided by S. So if you do not restrict this to the origin, which is S, and add a pole here, you will have a much more general controller, and you can always show the system or the controller, the first order controller, as AS plus B and CS plus D, which is the most general version of this. And you can see that choosing C1 and D0 will give you a PI controller. So you're working with a subset of phase lead, phase lag controller. The term phase lead or phase lag comes from the fact that this controller has a pole and a zero. Just one pole and one zero. And if one pole or 1, 0 is closer to the origin, then the system has a phase degree, which is basically a term that comes from the frequency domain. You can just go ahead and calculate the angle contribution here, and it will be positive or negative, and that will determine if it's a phase lead or phase lag controller. And this is also used in case of the root locus approach, since if you need to contribute more degree, if you remember, we had a angle condition that if a point on the S domain satisfies minus 180 or positive 180 degrees angle condition, it is on the root locus of this GS transfer function we are examining. If it's, let's say, minus 250, we need to add 70 degrees to it, so it should be on the root locus. This means that I need a phase lead controller since I have a positive angle contribution. It might be also possible that I'm at minus 150 and I need to take 30 degrees away from the angle. So this means that I will have a phase lag controller since I am negatively contributing to the angle condition here. So it's basically both a frequency domain or a root locus definition of the controller, and you can easily change the representation here. You can go ahead and calculate using AS plus B divided by CS plus D and convert it into K times S plus Z divided by S plus P. And if you don't know how to do it manually, you can use ZBK. That will give you exactly what we are looking for. Now, basically, designing a PID controller via these methods, or phase lead, phase lag, PD, PI, PID, all these controllers have their own structure, and you only need to know the structure of the controller. If you know the structure of the controller, then you can go ahead and design your closed loop with similar code. And let's see how we will attack this PID design problem. Let's go ahead and do that. Let me close these here. I will be 5 here. Clear CLC. Edit. Let's say run 1.m. Now, as always, clear and CLC will be my first line of code here. Now I am going to define the system here. Before that, I need to define the symbol here. Since S, then GSS is equal to, let's say, 100 divided by S times S plus 2, I guess, times S plus 5. Now, before I go ahead and do something else, I'm going to convert this automatically into a transfer function object by using numden of GSS, and then I will change the numerator into its coefficients, and I will convert it into double coefs, and then num, comma s, comma all coefficients, and then same for the denominator. And then GS will be TF num divided by that here. Okay, now I have defined my system in the control system toolbox, and I've converted into the transfer function object. Now, I want to design a PID controller. What should I do? Well, basically there are two approaches here. One would be defining poles and zeros, or basically gain and zeros, because the pole is at the origin. And I will define my controller as k times s plus z1 times s plus z2. Now this is the first approach. This is more suitable for the root locus approach, since you see where the 0 is or where both of the zeros are, and then you have s. You can just go ahead and treat your system. Since I'm looking at fss times gss, I can instead of looking at this problem like this here times this, you can see that I should calculate this here, and I have these zeros, and I'm adding the pole to the poles of the system, and then I have a gain. I need to add this gain here. So basically, if I look at this, I have to take this 100 value here. It should be here, 100 times k times that. There will be no other zero, but divided by this, and this s becomes here s squared. So this looks like if I'm actually using a different system for the root locus approach. You can see that this colored thing here can be a different system if I know z1 and z2. If I know the values of these zeros, basically I'm trying to design a p-type controller for a new or a different system. And I've mentioned that if some design point or desired point is not on the root locus, and you want to, and you're insisting on that design, it might be possible to add some zeros and poles to change and manipulate that root locus. Once you've done that, then you're using the new resulting root locus in order to design a p-type controller. Since you have decided on the zeros of the controller and you know where the pole is, you're adding these zeros and poles to the system, and the resulting new system becomes a system that you will use just for the calculation of the gain. So basically, when you have chosen your gain, then you're done with your controller design. So one approach is to use the root locus and examine the root locus, and if you have a desired point, you can look for the angle condition. Let's say we have 190 degrees of an angle. Then you can say that I need a phase lag type of controller. Then I can choose this angle as 10, and then I'm choosing a suitable point. I'm looking at the root locus, how the branches look, how can I choose this desired point, what happens to the remaining elements, and then if once I'm satisfied with the root locus that is created or generated, then I will add these zeros and poles, look at this root locus, calculate the gain. Calculating the gain is basically the design of a p-type controller. That's why the reason why we are starting with the p-type controller and focusing that much on the root locus in this course and in the previous course that is called Programming Techniques in Control. This is the reason why, because if you know root locus well, if you understand the basics of root locus, if you are able to use Matlab a little bit, then you might be able to, or you can just go ahead and use your knowledge and design every other controller that is in the family of PID controllers, PI controllers, PD controllers, whatever. So basically, I don't have to show every controller individually. I can just show you a code and give you the background on the controller structures or some aspects of the controllers. Then you should be able to be good on your own, because you have the knowledge that is required, the minimal knowledge that is required to design all the controllers, because they will be designed with the same mentality and almost the same code even. And you can see that. Since the most general version of this PID controller is a second-order controller structure, which can look like this: as squared plus bs plus c divided by ds squared plus es plus f. This is the most general transfer function or controller structure that I might want to use. This has another representation that I can show you. Looks like this. And then I will also have the poles here, P1 and P2. This is what the line 17 and 18 means. I have 2 poles and 2 zeros, and that's it. Basically, if I know how to choose these poles and zeros, I can add these poles and zeros to the system and go ahead and design a p-type controller. It sounds easy to choose these zeros and poles, but the actual problem lies in choosing these parameters here. And therefore, we have some approaches. One of them is a pole zero cancellation method. Of course, you're not trying to cancel your 0, Z1, and P1 in the controller, because if you do that, you will end up with a different controller. You will go ahead and cancel out Z1 and P1, which means that you will have Z1 equals P1. So I can just go ahead and plug in P1, which means that I can also get rid of this S plus P1 because it will cancel out. And you will see that I will have a first order transfer function or controller that most probably will represent a phase lead or phase lag controller. So if I'm really trying to design a second order controller, then canceling out the poles and zeros in the controller is not a good idea. But choosing one pole or zero of the system and using the controller to cancel that out might be a good idea. So what I mean by that is, basically, you can see that I have the system here. And it has poles at the origin, at -2, and at -5. So I can choose one of the stable poles because of internal stability and the things I've mentioned before in this lesson. All poles and zeros that are cancelled should be on the left-hand side, and S doesn't count on the left-hand side because it's neither on the left-hand side nor on the right-hand side. It is exactly in the middle. So this means that that's not a stable pole. It's marginally stable, by the way, because it is an integrator. And if you apply a step response, you will see that it will be a ramp function, which means that the ramp function isn't bounded, which means that this is not stable in that sense. So I cannot cancel, and I should not cancel a pole at the origin. It's not a good idea. And think about this. If you are trying to cancel something that's on the origin, and especially at the origin, and if it's a pole, and if you're placing a zero on top of it, that pole, what will happen if you have a slight error in your model? Basically, it might end up on the right-hand side, and that's why it's called basically marginal. Because a little error, something that will be changed, can affect that, and it will become instantly unstable, or it will be unbounded. Think of a sinusoidal signal or a filter that we've seen in the previous lectures. If you have a slight change in the parameter, it will become a sine wave that's unbounded, that will increase in its amplitude, and that's instability. So we don't want to do that. So basically, your pole zero cancellation is restricted on the left-hand side. And thinking about that, I can say that maybe I can choose a 0 here at 2. Also, I can also go ahead and choose another one at 5. And basically, getting rid of S plus 2 and S plus 5 will give me a nice result here. I will see what it will what it will show me in a second. And it should be pretty nice. You can see that. It's 100k divided by S squared. Of course, that's not all, because I have to calculate the closed loop by doing this here. But you get the idea. Since I have a third order system and my PID controller is a first order, my PID controller has just one pole, which means it's a first order controller. So having a closed loop of fourth order will be a challenge, but here TSS will be a Ziegler system, but of course not with an ideal system, and I will see that in a moment. Sorry. Now, let's go ahead and simplify TSS with simplified fraction. And let's use pretty to print our TSS here. Let's run that, and you can see that's 100k divided by s squared plus 100k. Now what's the problem? In terms of stability, nothing else, just think about stability. If you have the root table, let's try to emulate the process of creating a root table here. The s squared is 1, and then I will have some 100k and a 0 here, and basically 0 here and 100k. If I'm not wrong, this should be the root table. Now, what can I see from here? If you remember, we have a 0 here, so I'm not able to make them all positive. You are adding epsilon, etc., but I can also take the inverse Laplace transform here and see what it will give me. Make this as a comment. You can see that it will give me a sine wave, but the sine wave here has a gain and it's a sine. So basically it is bounded. Basically this is marginally stable, but it doesn't damp. So my damping ratio is 0 here, which means that zeta is 0, and I can see that for a fact that I have s squared plus 2 times zeta times omega n times s plus omega n squared. And I can immediately see, since I'm missing the s term, that zeta is 0. Omega n squared is 100k, and s squared is s squared. So basically zeta is 0. So that is not a desired thing here. And if I plot the root locus of this, which I'm by the way able to do, since it's only necessary to look at FSS times GSS, and I can plot the root locus of this, and I can see that this is basically 100k divided by s squared, which means that if I'm looking at R locus, I can use a transfer function. You should omit the k here. You will not use the k because you can't define the parameter k. And this should be the root locus that's representing my problem. Hopefully Matlab will be able to solve and show me that. Exactly. Now, what you can see is that I don't have the branches on the left-hand side, I don't have them on the right-hand side, they're exactly on j omega and minus j omega, which gives me this root locus. And this root locus tells me that if I'm in a filter design lesson or lecture, and if I'm trying to have an oscillator, then this will be a perfect solution set. But since I don't aim to design a oscillator, and I'm trying to design a system closed loop with certain transient dynamics and a tracking in the steady state, this is not ideal, and I'm not able to cancel out both zeros in order to get a stable closed loop system transfer function. Basically, in some cases this might be possible, but in our case it's not possible. So maybe I'm too greedy, so I am going to say that I have 1 0 left, and I'm just choosing at the moment randomly, and I say that this will not be anymore at 5. It can be variable, so it can change. So basically what I'm going to see will be the following. First of all, I'm looking at FSS, GSS, and you can see that I have a 100k times s plus z divided by s squared times s plus 5. Now, one of the s's comes from the controller itself, and the system has also an s term, so they are combined into s squared. I've cancelled out s plus 2, this means that I have s plus 5 left, and I'm adding a 0 at s plus z, so that's left there too. So at this point, I'm still not able to generate the root locus plot since I don't know where exactly my 0 is. But you can maybe make a sketch of your root locus using pen and paper and try to calculate where the zeta should be for your desired point and the angle condition. You can go ahead and choose the z such that my angle condition will be satisfied at the desired point. That is an alternative way of solving things. I'm going to show you the algebraic approach here. The algebraic approach uses equations to solve that. The root locus approach, where the name implies that too, will use the root locus angle condition, especially for being on the root locus. And if it's on the root locus, it's reachable with a k, and then you can go ahead and determine the k. So 2 steps, 2 conditions, and 2 unknowns. You can see that easily it's possible to solve for that. Now, I also should maybe look at that, and it wants a 10% overshoot and 4 seconds settling time. Now I can see that I maybe should define this 10% overshoot, which means that the zeta value should be minus log to the overshoot divided by square root of pi square plus logarithm of overshoot, the square of the logarithm term, not the overshoot, by the way. And this will give me 0.59, something like that, and omega n can be calculated by 4 divided by ts times zeta. You will say that this is not the original formula. Exactly, that's not it. If you use ts equals to 4 divided by zeta times omega n and trying to solve for omega n, you will get this here. So basically, I know my point. My design point is fairly obvious. I didn't type in zeta here. So by the way, let me just show you a quick thing here. Minus zeta times omega n gives me the real part of the design point. Omega d, which is damped frequency, can be calculated using square root of 1 minus zeta squared times omega n, and this will and what I'm trying to do here is I'm trying to design a controller that has that assigns 2 of the poles of the system at this pole pair here. Okay, I didn't define that. That's 4 seconds. If I run this part, hopefully there's something like TSA. Oh. Interesting. You can see that my design point is exactly here. And since zeta times omega n is equal to 1, and 4 divided by 1 gives me exactly 4, my settling time formula is satisfied. I'm not able to calculate the overshoot directly from the poles, but I might go ahead and look for the tangent of this here, the tangent of 1.3644 divided by 1, so basically this, and the cosine of this should give me my zeta value back. And this zeta value should be equal to this one, not the tangent, the inverse tangent, by the way. So okay, I can recover my zeta and omega n value, so I have verified that my poles are indeed here. So this is the Cartesian representation of my poles, and if you go ahead and look for the square root of sigma squared plus omega d squared, and if you look at a tan omega d divided by sigma, you will see that it will give me basically these values here. And since I have omega n, you can see that I have basically calculated my omega n. Now, this A10 gives me a degree, and I have to take the cosine in order to check what zeta is, since minus zeta omega n divided by square root of minus 1 minus the square of zeta gives me the tangent of that gives me this here, and so on and so forth. Now, you get the idea. Basically, I do not have to do this because you can go ahead and use these two as poles, and you will see that s minus sigma plus omega d times 1i times it's s minus sigma plus minus this time omega d times 1i will give me the exact solution that I'm looking for. Namely, this will be it. You can just go ahead and take note and try to maybe show that the line 16 will give line 17. It would be a good practice for you, so you will understand the relation between the second order transfer function, which we define all the time, and the time domain specifications, and that they match at this point. And it is very important that you do this practice on your own. Okay, now enough said. Now I will go ahead and define my PDS here, and therefore I need a sims s. I need I should start here. PDS is equal to s squared plus 2 times zeta times omega n times s plus omega n squared. Basically, I will look for the closed loop system here. That's not necessary anymore. So I have PDS and let's say VPA, PDS, 4, and for GTS. So, okay. I did delete somehow since S here. Now you can see that this is my polynomial, and this is my system closed loop transfer function. Now, it is a third order system. This means that I should add another pole to my PDS so that the degrees are equal, and then I'm able to solve the problem of coefficient equating of the coefficients. But if you see here, I will go ahead and solve this, but I have k times s and k times z terms, which are not that pretty for me, especially the k times z part of this expression, since it is also not easy on the human eye to calculate or predict the values of k and z individually, and it is also not a good idea to give it to Matlab to solve these types of expressions, because naturally these are or this polynomial is naturally not a linear coefficient polynomial. It is a nonlinear coefficient polynomial. Then Matlab goes ahead and chooses a nonlinear solver, and then things get messy, and I will give you a practical way or a better approach that you might want to use. Okay, now since I have looked at the problem, I can see that I need to define a PES, and before that I need to define another pole. So PES is equal to S plus P, and then my problem is obvious. I need to define my problem as coefficients of, what is it now? Oh, I didn't. Okay, I need to num them. Or you can, if you don't want the numerator, you can just go ahead and place a tilde here. But let me take the numerator, num them of TSS. Basically, I don't need this anymore, and I'm going to use them equal s, comma o should equal to, and I'm using two equal signs here, of the coefficients of PDS times PDS, and then comma s, comma all again. And as you remember, I might use for I equals 1 length problem, and then VPA problem, the ith element of the problem, VPA 4, maybe also display, and then and I can see my problem now. Now, since this first term is not that much needed, you might go ahead and start with 2, so you can see that I have 3 equations and some amount of unknowns. Now, P, K, and Z are the unknowns here, P, K, Z, so it's a 3 by 3 system, so I can solve for P, and obviously that should be 3, and plugging in 3 gives me 6, 6 plus this gives me 8.8, and divided by 100 gives me 0.088, something like that, and then just using that here, 100k is 8.8, times that should be this times 3, and then do the math, and it's possible to calculate that. Or Matlab is also able to solve this problem if I provide it here, and I can now go ahead and say what the p-val is. It is double solution point P, and then the same for all 3 unknowns, which is Z and K. I'm placing K-val and Z-val just to use different placeholders basically for the real values of P. I might want to check out what the P solution numerically was, or what the expression for P was. So I'm preserving that, and I'm just using placeholders for that. Now I can visualize what my parameters are, which I try to calculate just by looking at it. I can see that this is 3, I can see that this was the case, and Z is 0.9687. First of all, I can see that my p-val is positive, which is a nice information, since my PDS is stable. I know that this is stable because it has a zeta value of 0.59, and I have also assigned it omega n here. So this pole pair will give me always a stable pole pair. This polynomial will give me a stable pole pair. And PES is S plus P, and P should be positive, and it is positive, so I have a stable closed loop system. It might be possible that p-val is not positive, and then I will say that it is not possible to use this design method, or I should maybe update my time specifications. Maybe I should choose a different or even slower settling time, or a higher value for the overshoot. I should maybe let the system relax a little bit more. I am forcing the system too much with this control structure, since it's not possible to achieve that. It might be also that the controller is insufficient. I might be changed to a update or upgrade to a different controller structure, etc., etc. Now, I have now the design, so I can prepare my controller. I know that it will be something like this here. Now, k times, I will use convolution. Why I'm doing this, if you remember, I can use convolution to use the coefficients of polynomials in order to do the product of polynomials, and then get the coefficients of that. Now, you can go ahead and define a symbolic P1 and P2, and then multiply them, and then get the coefficients of the multiplication, and then again define the transfer function, but I'm going to use this approach here, which is way much easier. So we basically used what was it, 2. So I will give it 2, and then I also will give it z-val. So this is a placeholder for the other z value, which I've tried with 5, and I'm choosing this now, z-val. So this is my controller, and my closed loop will be feedback of fs times gs, comma 1, and then I can get the step response of TS and also maybe the Polynomial map or ZBK can be helpful for my closed loop design. I don't see the problem here. What is the problem? Line 38. K-val, of course, since K is a symbolic value. Now you can see that I have at least a stable solution, and it's not that bad, in my opinion. I have some zeros and poles here, and I can also see that my real part of my dominant pole was 1, sigma was 1, or half of this gives me also the real part of that, and I have also a 0 there, which is not ideal. I have a pole 0 cancellation, and I have another pole which is at -3. So basically this overshoot is directly explained by this 0 here, which is in the dominant region. And I said that the zeros in the dominant region are not that wanted and are dangerous, in fact. And you can see that here. I don't have 10% overshoot, I have 40% almost overshoot, which is not that ideal. So let this be a solution. I'm not hopefully going to close that. I am going to try a different solution here. I'm going to say that this is TS2. Now, you remember that we have used 2 for cancellation. Another option would be to cancel the pole at -5. I might want to do that. So hopefully I have just one solution. I will see that in a moment. And I will choose this as 5. Let's run this. Do we have a second figure? No, not at all. And it has a cancellation which I'm not happy of, and it has a p-val of 0, z-val of 0. We will see in a moment that this is not a good idea, but looks good. So maybe I should open this up and run this. Now you might say that this looks like a good idea, since it has a lesser value here. You can see that it has 10% overshoot, by the way. Delete that. It has 10% overshoot. It has a settling time that might be desirable here, since you can see that it has a 4. It should be 98, so it's pretty close. So 1.2 is also 0.2 is also the point where I'm looking for. So it's close basically. If you look at the exact value, not the tolerance band here, you will see that it is almost 4. It is a better solution, but a problem occurs at this point if I don't have the pole exactly at this here, but at a different point. Now, to illustrate that, hopefully I can take this transfer function here. Oh, I'm not able to take that there. Let me just go ahead and take it like this here. Let me redefine the transfer function. I will overwrite the original one here. Now, first let me show you how to get the same effect here. Convolution of 1, 5, no, sorry, this should be 100, comma, convolution of convolution, because I have 3 vectors to convolute, basically 1, 0, 1, 2, and 1, 5. Now this is basically the same. I'm going to run this, and it should not change anything here, and it didn't. You can see that this is the same. I didn't mess up anything. Now, keep in mind that this one is corresponding to the S value. Now, I will add a s that is slightly different. This is s plus 0.001. It is pretty close to the original system, but it's not the exact same. And I'm just trying that system. I'm not using this for design because in my mind, in my mathematical model, the system is represented with an ideal integrator. But in real life, there's a little heat going on, and it somehow affected the mathematical representation so that my pole moved slightly to the left to the stable area. Just slightly. This is not that much of a big deal in terms in numerical errors. Now you can see that it doesn't change the response that much. Now if I'm adding a little bit more, I will see that it should start the effect. Now I couldn't observe that. Let me try it again. You can see that it changes. Basically, this changes if I have a significant number there. But if not, it will give me the ideal looking solution here. Now, this is not a big deal if I'm doing that, but what happens if I have this 0 on the right here? You can see that it still stays on the stable side, but it might be possible that my realization doesn't match. So changing the model parameter might not be that crucial, but in the realization my controller has some heat going on. What will happen if I do this here? You can see that still on the stable side I have not that big of a deal. Let's try this with minus. Now somehow I'm not seeing this effect here. And why is that? What is fs? This here. Is Matlab doing stuff that I'm not aware of? Let's try this. Now I have this here. And I've changed my pool a little bit. But it's still, I have S here. Oh, I can, okay, I remember now. You're not noticing it for a different fact, okay. And I was a little bit skeptical, but we'll see in a moment. Now I am going to increase the time here. It should have a 400 time, so maybe let's take 1,000 here. Okay, didn't show me the effect. Still 4 divided by 0.001. It's 4,000, okay. What about 8,000 now? This is too much, but still. Still no effect. Interesting. Okay, maybe a little more should give me. Still not. Interesting. What is Matlab doing behind the scenes here? A more drastic change. Finally. Now, it was not that easy to see this effect, but it does affect. So, basically, in 100 seconds. Now the interesting part here is, and it was very hard to demonstrate that, but the interesting part is, for the first 100 seconds, the system looks stable, has a certain value, looks stable. And I'm increasing the time here, let's make it 150 seconds. Still no problem. Let me increase it to 200. I guess it takes approximately 400 seconds. Let's try it again. And after 400, you can see that there's a problem. So basically, 350 can be a better representation, hopefully. You can see that little ripple there. 300. There you see, after quite some time, and this is not that small, after certain minutes, like 5 minutes, 4 minutes, the system becomes unstable. Now let's try the same effect for the system, and it should be the same. And you can see that it's the same. Now how can I notice that? Basically, if I plug in a deviated version of the system, the controller, to the closed loop, I'm pulling out the exact mathematical model, and I'm plugging in the real model. So there should be a difference, and there might be a difference, because in the real world things don't have mathematical models that are represented with our representation transfer functions, because most of the time the values do not look this rounded, since you have 2, 0.1, 0.5, and during operation most of the time the mathematical model will be affected by the magnetic field, the temperature, the pressure. Everything will affect the mathematical model, and it will change slightly, maybe not that much, but slightly. So the basic idea, the basic message I'm trying to give here is that designing a pole zero cancellation at the origin is not a good idea. It takes quite some effort to deviate from s plus 1, but exactly at s, it's too close and it's too risky. If you're a little bit on the left, 0.1, 0.2, starting at 0.1, 0.2, depending on the system also, this effect may be not that big, but exactly at 0, you cannot guarantee that. So you shouldn't be designing this controller just for the fact that it has a zero cancellation at the marginal stability at the origin exactly. So it's not a good idea. It looks ideal, but in the real world you will see that this controller will cause you. Theoretically this is fine, but practically it's not practical, and you shouldn't use this. Now back to our topic here. So I've basically tried 2 of them. I can basically show what I mean by this, but hopefully, but I'm not going to be able to show that it will be -1. So, but let's try that. Let's try the version where I had 2 here and 2 here, and I designed that. I'm going to use figure 1 for that. And basically I'm using a different system representation. I'm using this controller here. Now you can see we still have this pole here, which will maybe eventually drive us away here. So the system itself is unstable. That is a huge deal here, and it will be the same for the controller. So for systems with this, it is not really that ideal. What I should do here, if I have this system, I should maybe model the system unstable and then try to design my controller. Now if I run this, it will also become like that, because I will always have this term here. It doesn't matter if it comes from the S, that it's in Fs, or if it's in GS. But if my pole at the origin is ideal, but my model doesn't have have the pole at 2, but 2.1, it will not change, since I will have a stable one here. You see what I mean by that? So basically, if I change the pole that I did cancel, if that's not modeled right, then if I have a pole at the origin and if I'm canceling it, it will be more dangerous. If I have a pole here and if it's not 2 but a little bit closer to the origin, it doesn't matter. Basically what I'm trying to say is this. Okay, now this basically shows how to design a pole zero cancellation controller. If you start with canceling S, you will end up with a PID controller. You can see that if I'm not using 2, but if I'm using S at the origin, this will cancel each other out, and I will have a K times S plus Z controller structure, which means that this isn't basically a PID controller, it is a PD controller, since the integrator part did cancel out each in itself, because it had a pole and a zero at the origin. So I've talked about the fact that it isn't a good idea to represent this controller if you're using the algebraic approach. Now, if you will use the root locus approach, feel free to use this representation, because you need to know where the zeros are, because you will use the angles and the distances of this zero, of the zeros and poles. So it's a good idea to represent your controller and even maybe your transfer function using pole zeros and gains. But if you're using the algebraic approach, which we are using in this code, it is not a good idea to use this representation, because it will give you nonlinear representations. So the problem itself is not nonlinear, but it will seem like that, and we've seen that here. I have k times z, which is not linear, it is nonlinear, and if I have more unknowns, it will show me a more sophisticated output, and it is not that readable, and I'm not be able to see what exactly will be the solutions. But you can see that this multiplication will be coming up more and more, and maybe calling this k times z a different thing will solve my solution. What I mean by that is, I know that this is s plus 2 here. In this case, it will be a little bit difficult, but most of the time, and I will not do this here, and I will show you in the next task here. Instead of showing this like multiplications, I might go ahead and say kd times s squared plus kp times s plus ki. Now, even the controller is linear now. The unknown linear combination of expressions fss will be used in a linear combination by, since GSS is known, I have a linear combination here. So it will basically give me a linear denominator expression that depends linearly on the parameters. So I will have a nice looking problem set that will be more readable, and Matlab will be also more powerful, since linear systems are powerful systems. We have powerful mathematical tools, and Matlab will be easily calculating things, and even you will be able to calculate things better. Since this will be, let's say, KD, then you can say that 100 times KD is this value. Maybe you can multiply this and divide by 0. But otherwise, you have to get the value of K and then plug it in here, divide and multiply it. So it's more complicated, and it's not needed in this case. Now, as I've said before, let me copy this here. So this was the solution of the first task here. We did design a PID controller by a pole zero cancellation. We chose S, and it was not a good idea. Keep that in mind because it's at the origin. We chose -2. It did work. -5 did work. We tried to choose both of them. And this might be also possible, but it didn't work because we were on the j omega axis. You might want to use some combinations of these, or s plus 5 and s, but since every time you will, in the other iterations, you will also always have this s term here, that means that it's from the starting point not a good idea, so I'm not showing that. Basically, for a third order system, you can take the combination 3, 2, and calculate how much possibilities there are, how much different possibilities are there, and then for 3, 1, there are basically, for the combination 3, 1, you can just choose 3 different poles here. For the other one, there were I guess also 3 different, because the combination 3, 2 gives also 3. So you have basically 6 possibilities, but since one of the, was it 6 now? Yeah. You have the s at the origin, it narrates down to 2 meaningful possibilities, namely just choosing s plus 1 or s plus 5, and that's it. You are not able to choose both of them at once, or you are not able to contain s in the pole zero cancellation. So that's that. So we have seen how to use this pole zero cancellation, and this is maybe a little bit about brainstorming, because you look at the system, you try to guess what will happen if I cancel this, and the root locus will adapt itself like that, and I will try to add maybe a 0 there, and then place the pole here. And this is a little bit more of a brainstorming task, since you will use the root locus, and different root locuses will be generated by your actions. So taking actions carefully might be a possibility. Sometimes this pole zero cancellation can be very helpful, sometimes it could be very painful, depends on the situation. Now, how can I design a PID controller by a tabulation? Now, what do we mean by tabulation actually? Now, we've seen that in A we had a 3 unknown and 3 equation system, so we were able to solve just one. But we also have seen at the beginning of this lesson that we can have a parametric solution if we have just one variable that is freely changeable and choosable arbitrarily. So basically, for a PID controller that will be designed for the system in a moment, we most probably will have a parametric solution that's implied here. This implication comes from the tabulation. If there's no free parameter, you can't generate the table, basically. And the other word for tabulation is gridding. So you can grid a certain interval. You can take samples of in an interval and try those and look at the results. Now, basically what we will do is we will iterate here. We will try to look for an interval and look at the results and choose one of those solutions or solution candidates. So basically I need a big table where I will save valuable data that concerns the closed loop, and I will try to choose one of them, because changing a parameter will change the root locus so that it will change the gain, and there is a lot of change involved here. So let's attack the problem directly, and you will see what I mean by that in a second. Now, I will go ahead and copy the whole thing here and paste it in here and save it as run2. Now, I'm not going to define this as this, but as I've mentioned earlier, I will use kd times s squared plus kp times s plus ki. And naturally, my parameters are not k and z. They are k, p, k, I, and kd. So basically, the PID parameters are k, p, k, I, and kd, and I'm looking for those parameters. Now, I have a third order system. I'm adding a pole. It will be a fourth order system. Now things will be changing since I have used a cancellation, a pole zero cancellation during the design in A. I did end up with a third order system since my controller was adding 1 degree but also canceling a pole of the system, so the degree didn't change. The closed loop was the same as the open loop. So I had the same degree. Here I'm not canceling anything, I'm adding 2 zeros and 1 pole. As in the case in the PID controller design, I am basically adding a pole to the system. The amount of zeros doesn't affect the degree of the system for now. Basically, I will have a fourth order system. Now this is another challenge, since adding 2 poles is much more difficult than adding just 1 pole. Now, you would say this is a trivial statement. You might think that, but it's not. It's not. Because it is not the same amount of complexity involved here. If you add just 1 pole, you're restricted on R, which means that you have just 1 degree. But if you add 2 poles, and if they can move freely, this means that I might have 4 unknowns for these 2 poles. What I mean by that is, do not forget that we are working in the S domain, so these are not only values, these are complex values. So they have real and imaginary values. So this is basically a pair of 2 unknowns. If I'm adding a pole, I'm adding a pair of 2 unknowns. Why isn't that the case for, let's say, 1 degree increment? So if I'm just adding 1 pole, because that pole is restricted to the real values. It is restricted to the real values for the fact that a system of third order should be, if it's a real system, if it's a real world application, it shouldn't have imaginary values in the transfer function. Now, let me show you what I mean by that. Let's say we have a, let's say polynomial 1, 2, and 1. It is s squared plus 2s plus 1. And let's look at the convolution where I have this polynomial and a root at 1. So what I will basically get is fairly easy. I will get this here, which means that since there are 4 coefficients, it's a third order system, a polynomial. S cubed plus 3s squared plus 3s plus 1 is the polynomial that I'm looking for. Okay, nice. Now, what happens if I have a complex value here? 1 plus 1i. This is not possible. And I will see that since I will have some imaginary values in the coefficients. So this is basically s cubed plus 3 plus 1i s squared plus 3 plus 2i s plus 1 plus 1i. So I have the imaginary values, which is not possible for the family of systems I'm trying to examine. So if you have a degree that is odd, if you have odd degrees, you have to add the at least one pole that will be a real value. It shouldn't have an imaginary. But if I'm adding 2 values, then I will have a conjugate pair here, which makes it possible so that I have real values. And that's also the reason behind the idea that all second order or all conjugate pairs
are forming a real polynomial or are a solution of the real polynomial. So basically, what I try to say here is that I don't have just one unknown as it was for just one pole. I have basically, if you look for the interdependence and the conjugacy of these complex values, you have three unknowns basically, or two unknowns basically, not one. And this is, and they have a relation. That's why the reason we have just two unknowns. It might have been a plus bi and a minus bi. But it might have been also a plus bi times c plus di. So a, b, c, d will give me 4, but in this case they should be conjugate pairs, so they should have basically the same real and imaginary values. But the complexity here, what I'm trying to say is that it's a big deal. It's a big deal for Matlab especially. Since we are using Matlab to calculate our design parameters, it is a big deal for Matlab. So, how can I solve this? Well, basically, and by three unknowns, what I mean by three unknowns will be obvious in a minute. Basically, defining polynomials will be a better idea than defining the root of these polynomials. So, if I'm using s plus p, I'm defining the root of the polynomial. If I have a first order PES here, if I have this here, it's showing both. P is the solution of the polynomial, it's the root, and it's also constructing the polynomial itself. But in case of a second order polynomial, it might be a better idea to use, and I will use it basically here, A, B, and C if it's necessary. If A is not necessary, maybe A and B. So I was basically using S plus A, and now I will use A times S squared plus A times S plus B. So A and B pairs, and it might be CS squared plus AS plus B, but I will use this as my polynomial since I know for a fact that my system should generate coefficients with high order term 1. This shows me that I have A and B as parameters, which is nice, and A and B are real values. But the solution can be complex conjugate pairs. Because of the discriminant b squared minus 4ac squared, etc., etc., you can see that this will represent. This can represent this can represent a conjugate pair. This can represent two exactly same real values, overlapped solution, or it might represent different real value solutions. So. If you define it using, let's say, PES, S plus A times S plus P, it is, and if you restrict A and B to be real, then you are looking just at a subset of solutions. So it's not a good idea to use A and B so that they are roots. Or you can assume A and B to be complex conjugates, but Matlab will try also the other values that are not complex, that are not forming a real polynomial, or where A and B are not conjugates. So it's not a good idea basically, and we should go ahead and use this generalized polynomial coefficient method. And why am I doing this? Well, if you remember, the closed loop PCS characteristic equation was formed like this: numerator times numerator of the controller plus denominator times denominator of the controller. And you can go ahead and check that. You can just take a pen and paper and check if this is true or not. Now, if you look at this, I know the numerator and I know the denominator of the system transfer function, but the unknowns are included in numerator f, so the numerator of the controller, and in denominator f, which is the denominator of the controller, which corresponds to the poles of the controller. So basically what I'm trying to say is that I don't know the gain of the controller, I don't know the numerator of the controller, and I'm not aware of the poles of the controller. If this was the case, I would have just used the controller. Since I'm trying to design the controller, I don't know these values. But if I use PDS, and since PDS is known, and I will multiply them here, you can see that. So this means that I will have a linear combination of a linear combination of coefficients, which eventually will give me a linear combination of A and B. So this part will be linear. So the right-hand side will be linear if I use A and B. If not, it will include the A square plus B square terms that stems from the imaginary parts of the poles, and etc. etc. You know what I mean. So basically, this representation is the most linear version that I can come up with, and I will use this. It is the same here. Since I will have this as the numerator here, it will come here, and I know that the denominator is s. Basically, I can replace this with s. I will have a linear term here. So the left-hand side will also be linear. So having linear equations can also give me the ability to express my solution in a matrix representation, and then just go ahead and take the inverse of that using a calculator, and just go ahead and calculate my relation between the parameters. So this is a nice simplification that is available to you, and you should go ahead and try to define everything linear when you're using, and if you're using, the algebraic approach. So that's very important. Keep that in mind if you want to design a controller, and if you are not using the root locus at the design process, then you should go ahead and try the most linear version of everything. You should define everything as linear as possible. So what I mean by as linear as possible is just linear. You get, hopefully it is understood what I mean. Okay, now enough talk, let's do some design. Let's carry out the design process here. Basically, I have the overshoot setting time. I have calculated my zeta and omega n, which directly relates to my PDS and gives me the exact polynomial. Then I have defined my system. I also directly converted into the transfer function object, since I will need this for evaluation of the step response. Once I've done that, I know that I will be adding a degree to the system, and the system in hand is a third order system, which means that my closed loop will be a fourth order system. I have 2 poles in the PDS, so I will add 2 more poles. And I hope that both these poles and all the zeros will be far away from the dominant pole pair, which is not that simple. Now, I have also defined my controller parameters. My controller structure is defined here. I have the closed loop system. I have the numerator and denominator. I have the problem, and I have PDS times PDS, and the denominator, they should be equal. And before I'm going to solve everything, I will just see what the problem looks like. And as you can see, I have a linear combination of A and B everywhere on the right hand side, and also linear combinations of KP, KD, and KI. For this system, we also have a very nice result here. Now, before I move on, what do you think about A and B? What conditions can I come up with so that A and B will be chosen that way, and the closed loop system will be stable, since the stability of the closed loop system is my first priority. If I don't have a stable system, then the design is not possible. Before I am trying to set the setting value and overshoot and etc., I should first assure that my family of controllers should be stable. And why do I call it a family of controllers? Since I have A, B, I have two parameters there, and I have KD, KP, and K, I have three parameters there, which makes 5 unknown parameters, but I have only 4 equations, which means that one parameter can be chosen freely. And it's definitely not A, because A is already 5. So basically, I have infinite amount of solutions, but how should I choose A and B if you look at this residue polynomial? Well, since it's a second-order transfer function, and since I can say that the sum of the roots here is calculated with minus b divided by a, and since the multiplication here can be divided by b, I guess. I'm sorry, this should be minus a. Since it's not as squared plus bs plus c, it is s squared plus as plus b, and a, b are conflicting here, but that's it. Now, I can see that if a is positive, then my sum of my poles will be negative, so they will be stable. So for stability, a should be positive. And since multiplication is b, if b is positive, that means that both have the same sign. So basically, having b positive is also needed for stability. So I can see that having a and b positive will give me a positive solution. Another way of thinking can be, again, with the root table here, and you will just see that it is fairly easy. This will be 1, this will be A, this will be B, and this will be B. So 1 is positive, so A and B should be positive too, for stability. Basically, I can calculate that A is 5, and maybe B should be calculated. So if I look for A, B, and 2 of the parameters of the controller, then one of the controller parameters will be left as a free variable, and I can then choose a certain interval at least for this control parameter, hopefully, if it exists. Then I should end up with a combination of controller parameters that should give me at least stable solutions. And from that point, I can try to look for the settling time and overshoot, and which parameter combination or which combination of parameters gives me the best solution. I will use a table for that. Now, I can solve the problem, but I need to give it the parameters for which I want to solve it. So I said that A and B should be solved for starting point. And maybe I will look for KD and KI. And KP will be the free parameter. So that's a possibility. Or I can say, okay, let me get KP and KI. And KD is the free parameter. So if you look at the controller, if KD is a free parameter, you can use this KD and factor it out, and you will see that S squared plus KP divided by KD S plus KI divided by KD will give me the numerator of the controller. And if I know KP and if I know KD, if I know KP and KI, basically I might assume that I somehow know where the zeros are, and I'm looking for the root locus gain or the gain of the controller, since it very much looks like this here. So I'm just then scaling the gain here. You can think of that of this like that. Well, let's just choose randomly. It doesn't matter really. So let's look at Sol A, and with VPA I will look for the other solutions, and KP and KI. can see that this was 5, and I did also calculate that, which wasn't a big deal. And also I can see that my B parameter is like this. So this means that having a positive KD value or a value of minus 2.862 divided by 100, KD should be bigger than that, so I will have a stable solution. Why do I say that? Since A and B should be positive, and A is naturally positive, and B can be determined by this here, I can see that I should choose just positive values. So choosing positive values for KD will be enough, since this is not that big of a number. Divided by 0 gives me approximately something near 0, so yeah, I can just assume that this will be positive. And most of the time, if you don't want adverse effects, you should look at this numerator, and you can say that KD, KP, and KI most of the time, probably should be positive, since for the same fact that A and B are positive, this should give me a stable pole pair, or a stable root pair, or zeros that are on the left half plane, since I don't want to have zeros on the right half plane. Now, poles on the right half plane are causing instability, but zeros on the right half plane do not cause instability, but adverse effects that are not really that wanted in control system design. Now, for a certain KD value, I'm also able to look where my pole is and where everything is. Now, I can see that if I increase B as much as possible, I'm basically placing the pole as further away as possible for B. I'm not sure about the pole, but I'm increasing something in the polynomial, and that is B. And unfortunately, if I'm not wrong, hopefully I'm not wrong, my real values of the residue poles are minus 5. Minus 5 divided by 2. So minus 2.5. I'm not able to cross the line minus 2.5 to the left. That's unfortunate. So this will restrict me to a very slow design, since hopefully I'm talking here by neglecting the zeros, by not taking zeros into account, just in terms of poles. If I had a old pole system in the closed loop, then the things that I'm saying would be happening. So my residue poles are still at minus 2.5, and that's a fact. Now, if I increase B, the oscillation of those poles will increase, which means that the zeta value will decrease. So this needs a little bit of experience in controller design. You might not be able to directly tell this, but after some time you should be starting to look at the system, look at your equations, and try to evaluate what will be happening and predict what will be happening. Now, let's just directly go to the solution, and then maybe we might talk about this. Now, I need positive parameters to look at, since those will give me a stable closed-loop system. Now, let's say we want to have a table, and I will define it here. This table will include data, since I have a parameter KD that can be changed in the positive interval. Let's say 0 and 100. In the interval of 0 and 100, I will change KD, and everything in the closed loop will change. So I want to track that. I want to see what's happening. In order to do that, I might use a table that will guide me through these infinite amount of solutions. It will hopefully guide me through this finite set, the finite subset of infinite solutions, and hopefully it will show me a applicable controller parameter set. Now, what will be the table what will be the table in terms of structure? Well, now every row should be a solution or a point in the infinite subset, in the finite subset here. It should be just one design point. So a parameter pair should be represented in the row. So the amount of columns will be depending on what I want to put in the table. So let me just note here that I might want to use KD, KP, and KI as parameters. I might also look at A and B, these parameters. You can also go ahead and place the raised folds here. But let's make a minimal table. So let's just take controller parameters. Since once I have KD, KP, and KI, I can define my FS. I can look at the closed loop, and I can use the step info function of the control system toolbox in order to get some overshoot and settling time values. So I might get some experimental settling time and overshoot values that are coming from the experimental side. So I will try to validate that. Let's keep it at that. So I have basically 5 columns here. 1, 2, 3, 4, 5. How many rows? Well, what will be the interval, KD interval? Let's say KD interval. And let's define an interval. Let's start with 0.1. Let's go 0.1 up to 0.2. Now, if you're writing a code, keep it as simple as possible, since it is easy to debug them. Now I will use the length because I have 0.1 and 0.2, which gives me only 2 points here in the finite subset of controllers. So I will have 2 rows, each row corresponding to each KD value. So I can just go ahead and calculate this by using KD interval. Interval. There we go. Now, once I'm done with that, I will use the for loop to move through these rows. So it should be also the KD interval, since I'm looking point by point what's happening, and then I will just save it in the table. Basically, my first task here is to, first of all, I will define A, V as solve point A, B, V as solve dot B. So I'm defining some placeholders here, KPV as solve point KP, and KIV equals solve point KI. Now, first of all, the KD value, I will use val for numeric variables, is KD interval, the ith element of this array. And then I will have KP val, which will be calculated using double and sub, since it's a parametric expression, a symbolic expression. And then I will have KPV, which is a placeholder for the solution.kp. And I want to change the KP value. I want to change the KD value, since it's a, as you can see here, it's depending on KD, and the KD value will be KD val here. I will repeat this for KI. I do not need to repeat it for anything else because I have the param controller defined at this point. So I can go ahead and use fs, tf, and provide the parameters here. I can say kd val, comma, ki val, kp val, comma, ki val. and putting a semicolon. And I have defined yes previously, I remember that. Okay, basically at this point I can construct my feedback fs times gs comma 1, and I can use info equals step info. I'm not even looking for the graphical representation of the step response here, I'm just giving it the step info. So info.overshoot and info.settling time will give me the results here. Now, let's run this. I can see that, and we have some error. Why is that? Uncurrent functional variable KD interval. So, line 38. Interval. Okay. Spelling error. KPD val. What's happening there? KD val, KP val, KI val. Spelling errors are annoying. Okay, I have some answers, which means that these two belong to the first point, these two belong to the second point, and as you can see, the overshoot is given as percentage. I might want to divide to 100 in order to get a value between 0 and 1, and I have a settling time which looks not that bad. So basically, at this point, I can go ahead and generate my table and look at that. Let's first go on and do that. Now, since I'm done here with all the required data, I have everything ready, now I can choose my table row, which is the ith row and all columns, and I will fill data here. You might want to use I, 1, I, 2, or you can also give an array and say it and put in a column there. Now, remember this here, 36. So KD val, comma KP val, comma KI val, comma settling time and overshoot. So maybe overshoot experimental, and then settling time experimental. There we go. Now I can say settling time or experimental overshoot experimental. Once I'm done with that, I will then see what the table looks like. Now you can see I have a nice table here. Let's generate it again. Now you can see that 0.0, 0.2 makes sense, and this is my KP, KI, and then I have the settling time and overshoot values. Now, here I can see that my settling time was around 4. That's not bad, but my overshoot is too much, and it seems like if I increase my KD value here, it should decrease the overshoot, but my settling time is also decreased, so this might also be not that ideal. But we will see that if I am gridding it in a bigger interval. You can also make it like that, or you can also adapt the code so that it will give you row by row, but that will take much more time. So letting Matlab do its job and then visualizing data is always faster. And you can see that my overshoot doesn't become that much better here, and it increases where my settling time decreases. So it's not a good idea to choose it in this interval. It seems like I might be sticking here somewhere. Or it can also be possible if I use this here and this here. It might also be possible that I need to choose a different interval. But it doesn't seem like that since it is increasing and increasing. Maybe let's give it a even higher value here. Let's try with 50 and 70. I am not unfortunately able to choose a direct interval that is very big, because the computer, Matlab, will try its best, but it's not that easy to grid the whole real axis, even if it's only restricted to the positive real axis, since there will be at some point too much data here. And keep in mind that I am always using substitute here several times, which is not ideal. And I'm using step info, which basically uses the step response, so it calculates step in the background, so you are basically repeating simulations over and over again. So basically, this is a bit of an issue here. Now I can see that my ideal solution seems to be in the area where I have this here. So I should maybe grid that area a little bit better. So what you should do here is to try the biggest interval with less samples, and then focus on an ideal seeming area. You can see that it takes too much time really. To focus on a part of that interval and grid a little bit better and better and better, and at some point you will end up with an ideal solution. Now I can now see that I have reached the stability margin also, and I didn't calculate it, but if you calculate the interval, you will see that at this point you have unstable solutions, but here you have a solution that might be a good idea. So the first solution here is not that bad. Maybe I should start reading with 3, and in order to speed up, let's give it a 1 or even 0.2 here. And you can go ahead and solve this, but I may add an indicator on the quality of my solution. So how good is my solution? I should evaluate that. And I can do that if I would have had just one here, just one parameter, design parameter. I would just use the absolute value of the error between the settling time I was supposed to accomplish and the experimental result. I would take the difference, I would use the absolute value, and I might also want to convert it into percentage by dividing it into TS. So what I mean by that is I might have just calculated an error here, and therefore I need to increase the column for ticks, since I will keep track of this error, and I would have used the absolute value of TS and TSE, which represents my experimental testing time, and I would have just placed this here and run this again. Let's run it again. I will have one more column here, and you can see that this somehow gives me the absolute error here for the settling time. Now I was trying to design a settling time with 4, so there's a margin of 0.15. If I have 9, I have 5.2, because adding 4 gives me this here. But this doesn't give me that much of a good result, because somehow it is not really that easy to see exactly what the percentage is, because the percentage is more important than just the gap here, because it can be misleading here. So if I divide this by TS, this should give me the percentage here. So 3% error, 130% error, etc. Now 12% error or 2.27% error. This will give me that, and you can see that. But this is only the error in, if I'm looking at this setting time here. So I might also generate another error, let's say error 2, and this can be about the overshoot, and I will do the same. I will choose the overshoot here, choose the experimental one, and I will divide into OS. So keep in mind that I'm dividing to the specification, not the experimental data, because the specification does not change, but the experimental data will change at every row. So it's not feasible to divide into this value, because this is the experimental data, but I'm always dividing into 4 for every row. So that makes it a valid comparison tool. Now I have to extend this to 7, and I might see the error 2 here. Let's calculate that. Now this 7th column is here. Maybe try it again with a exactly. Now I have 2 indicators for 2 different specifications. One is for settling time, one is for overshoot, and I can see that in terms of overshoot, this solution looks ideal, but in terms of settling time, this solution looks ideal. Now, I might choose one of these, but how can I combine these indicators so that I have just one indicator that tells me the quality, and I will have a certain weight to each specification. So maybe I'm interested in 50%, 50% in terms of the indicators, which means that the amount of error in settling time should be equal to the amount of error in the overshoot. So everything is equal. So this will be a 50%, 50%, a 50-50 situation here. So in order to accomplish that, I might combine these two. Since I have normalized them, this process of getting rid of the units, I can just have some neutral values that will represent a percentage. Now I can combine settling time, which is seconds, and overshoot, which is percentage. I can't combine apple and something else. I should combine apple with apple, which means that they should be of the same type. So I'm normalizing, getting rid of the units, and I'm forcing them to be between 0 and 1. It might be -1 and 1, or even it can have some values of 2, but that's the penalty I'm also assigning there. If it's between 0 and 1, and if it's ideally 0, that's 0 penalty. But the value that will be represented in these 2 columns is basically the penalty for me. The lesser the value, the more ideal. If it's something like 20, then that's too far away from the ideal solution, and I'm of course not interested in that. So values between 0 and 1 are the ideal ones. I might also enable the ability to have faster solutions, which means that the settling time may be negative, maybe absolute isn't a good idea there, or maybe I should look for the sign and include the sign. That is possible. So, we might look at that later. But this can be combined so that I have just one error, and let's say error 1 and error 2, and I will combine them with 0.5 times error 1 plus 0.5 times error 2. So I will just keep track of this, and I will not put the other ones there, and it will become 6 here. So basically, looking at the table now will show me just one indicator that assigns both settling time and overshoot 50% of indicator weight, and I have the ideal solution, which is this one here. And then my solution becomes more ideal. Now let's see what happens if I change these percentages, and keep in mind that you can combine any amount of indicators with this combination method, but keep in mind that your coefficients here should be summing to 1. So if you sum the coefficients here, they should give you 1, and keep your errors or indicators between 0 and 1. So they should be normalized, and their combination should be so that the weights are the sum of the weights equals 1. Otherwise, this isn't a nice combination method, and this way of combining things is called the convex combination, and it preserves some properties that we're interested in. Well, now, what will happen if I want to increase the weight of the settling time? Let's say 90% of the settling time and 10% of the overshoot, which means that I will allow the system to overshoot but the settling time is more important for me. So let's see how the ideal solution is chosen here. Basically, my ideal solution is here, because the settling time is the closest here. Even though I have overshoot, which is 10%. Let's try an even drastical setup here. And it gives me still this one. This here somehow wants to become ideal too. This is almost there. Or this one is especially ideal, I guess. That should be the minimum of that. Exactly. This is not the ideal solution, where the settling time is closer to 4. You can see that. Now this is close, but this is closer. So if I want to exactly choose according to the settling time, I can use this combination. But you see that it has a high value of overshoot. So the penalty on overshoot is neglected, sort of. Now, if I change it around, I will see now that the optimal solution should change. Now basically I can see now that the settling time doesn't play a role here, and my solution is here. Let me just try to change the interval just a little bit. Let's adjust it a little bit. I guess 0.25 and 0.15 should maybe solve my issue. 0.2, maybe 0.152, I don't know. Let's try this here. Okay, more 25 plus 15 gives me 40, I guess. Now I can still see that this one is still the best solution. The more it gets to the instability area, the better the solution is, unfortunately. But you get the idea, and if you choose different weights, it will give me a different result here. So this is kind of called Pareto optimal. It has a combination in it. It uses weights here. So basically these solutions may be not that bad compared to this one here, but I'm not paying attention to settling time that much, because I have 50% and 50% here. So it depends on your needs. Sorry, this one is the ideal solution, since it's these parameters are really close to each other. Well, you can see that this has a reasonable settling time, but still a high overshoot, but it seems more reasonable than the first solution here. But they are not that far away, keep that in mind. So now I can automatically acquire what the solution is by using minimum of the nth row here, or you can also put in the column size here. This is taking all the rows and looks for, it's basically getting this here, this last column here. So I'm saying the last column, get all the rows, and take the minimum. Now, as far as I know, it should be val and index. So I'm going to try this here, and it should give me the index. You can read the documentation of min. So index 2, the second is the ideal one, so I will say row equals to the table, the index row, and give me all columns now. Since all the columns will include my KP, KI, and KD values. It is possible to write a code that will get the solution from here, or you can also save these here, but I'm not interested in that. I'm just going to use this, and I know that my controller should be constructed as follows. You can extract every parameter individually, but I have aligned them so that I can take the first 3 elements and it will give me automatically the numerator. So basically, this table here has a numerator in it. This will be the numerator, or this will be the numerator, depending on the solution which you want to choose. I will just get row 1, 2, 3, the first 3 rows, and then just provide 1 and 0 here. And this will be my transfer function. Now I can go ahead and copy this here. And also I can just say step and choose this solution here. And I can just get rid of everything else. And let's run this. So it creates a table, it looks through the table, and hopefully gives me a nice result that looks like this. So you can see that it has a 4 second settling time, which is not that bad, but the overshoot here is a little bit off the limits. Since I was aiming for 10%, which is this line here, it got a little bit bigger. So if I want to somehow solve this, I might say the first one was the settling time, the second one was the overshoot. Am I right? Yep. So I might try this combination, which should have a better interval here. Let's give it a little bigger interval. Wait a little bit, and hopefully we will have a good result. Now I didn't type in figure 1, so it doesn't pop up. Maybe choosing that is a good idea. Let's try that. It is also possible to narrate down so that you have sort of ideal solutions. It is also possible to, let's say, do something like this. I can say figure 1, clear F, hold on, grid on, something like this. And once I've cleared that, I might solve for this, and I can say that this is my, this is red, as far as I remember. Okay, the grid did go away. And then K, and without clearing, just go ahead and change these weights here. You might also do this with code. You can just use a 4 outside of this 4 to change for certain combinations. And we have this, and you can now compare and see the result here. My setting time for the red one, my setting time for the black one are slightly different, but in terms of the 2% or 5% tolerance band, it seems not that big of a deal. But practically it is a big deal because the first one, the black one, is settling down faster and the red one is not. But also I can see that my overshoot did decrease if I've chosen more for the overshoot as a weight. Now I can also see the reason behind this. Maybe we should repeat this for the polynomial map here. Let's say figure 2, and let's say PZ map here, and I will have a certain color for that. Let's have K, and let's say figure 1, clear figure, hold on, then figure 2, clear figure and hold on. And once I've done that, I've generated 2 figures here. I'm going to say run 2, that's one solution. And then I will have red and red for the case where I am caring more about the overshoot than the setting time. And run it back again, and it should combine these 2 graphics. As I've said before, you can go ahead and choose to code it with a for loop, but it depends on your choice. Now, I can see now that my combination with the red one has a better pole zero cancellation, even though the pole zeros are a little bit more dominant. And I'm assuming that in the table, the higher I go to the limit where I have the j omega axis, the stability. If you remember, we had some number outputs, non-outputs. If you are decreasing your KD value, you're approaching here the stability margin, but your pole zero cancellation gets better and better, and that's the reason why we had a better response. And if I'm going to do that, it will become more and more like a 10% overshoot and 4 seconds setting time. And also this pole zero map will look better and better, and you can see, and hopefully this zero will not enter the domain, the dominant domain. So these are a little bit far to the left, and I have a pole zero cancellation near the origin, which is not that ideal, but somehow does the job. The black one has a not that of an ideal cancellation, and I can see the effect that the system becomes a little bit slow here, has more overshoot since we have a zero in the dominant region, etc., etc. Now, this second task is completed at this point. I will show you this Ziegler-Nichols thing here, and then you can just go ahead and look at this PDF for the phase lead controller via the pole zero cancellation and the tabulation, but it's the same thing repeated. But of course, phase lead controllers or phase lag controllers or different structures of controllers will have different properties that you should maybe evaluate and try to design and look what the difference are. But most of the time, PID type controllers are a little bit different than phase lead and phase lag controllers for the fact that we are placing an integrator in the forward path, which is a big deal in terms of reference tracking, in terms of ramp tracking, step tracking, etc., and in terms of the service rejection. It is very important to have a integrator in the forward path, which means that somehow you have a integral of the error somewhere, or if it's needed, the double integral of the error. So we will come to that in the upcoming lectures. Well, as I've said before, phase lead and phase lag controllers might have steady state errors, but the PID controller most of the time, if there is no zero at the origin, will have zero steady state error since they include an integrator in the forward path. This is also for the PI controller, but the PD controller and P-type controllers do not guarantee that since they have no integrator in the forward path. Well, now, since we did extend our time very much, I will show you my PDF that I've prepared here, which is a bit more detailed. It might be different than what you would expect, since I did prepare that way before this lecture, so I didn't change, but basically the idea is the same. You can see that the solution is also around the same point here, and you can see the closed loop, you can see the combination of the indicators. I said that if you combine this error, both of the errors like that. You can also see the residue polynomial stability, the closed loop, an example table. What I mean here, and what I've talked here today about, is that it is not a good idea, and I have still not updated my table here, or I am demonstrating here that a different version is like this, and you shouldn't do this. This is not the ideal way, because you have the real and imaginary parts. These are the coefficients Z1 and Z2. Do not think that this is unstable. These should be positive, since S plus Z1 is equal to 0, so S equals minus Z1, so the negative versions of these are the real solutions. then you have overshoot, the objective, that's going to be called error objective, whatever you want. And you can see some root locus plots that are accommodating these plots, since we can look at this in the root locus, so it will give us an idea of the dominant pole placement. You can see that the PID controller using the Ziegler-Nichols. Now, the thing with Ziegler-Nichols is it is very easy, but the only thing that you should do is you should have some parameters about the system and some basic parameters. One of them is the gain that is necessary to drive the system to marginal stability or to oscillation. So basically, you go into your laboratory, you have a motor, you have a temperature system, you have a liquid control system, whatever. You try to use a p-type controller, or you try to plot the root locus plot of this, and you're trying to get the point where the system becomes oscillating, becomes marginally stable. So the thing is, you're applying a step input, and your output is oscillating between certain two values. So this is the marginal stability point, and the Ziegler-Nichols needs the stability point in order to not extend to the right of this. And also, you need the frequency, or even the period, the time period of this oscillation signal. So you need the critical gain, which is driving the system in the closed loop to oscillation, to marginal stability, and the frequency of that. So basically the crossing point on the j omega axis. These two parameters, k and pau, will be then used with formulas that are giving you directly PID parameters. So that's it. There's no tabulation, no pole zero cancellation, nothing at all. You're just plugging in the values into formulas that are derived from Ziegler and Nichols, and they have some theoretical background on that, why they can provide you with general parameters or formulas for general parameters just by using the stability margin. They're just giving you a standard PID controller that has a distinct and very well-known step response. If you're looking at some books, and I did actually said that you should check out the book where the book of Ogata, I assume. I said that you should check that out. Hopefully you did. And let me just find it for a second. It was on there. I don't remember. This book here. Does it have that on it? Oh, that was not the book we had there. Maybe I have another control book. Most of the control books have these nice plot that we are familiar with. I'm trying to find a control book that has that. Does this one have that? Interesting. I can generate that plot for you, and I will do it in a second. But interestingly, I'm not finding it. Hopefully this one has that. Nope. No. Now, your response will look like something like this, and I will show you how it will look like. Let's say omega n is 1. You will have something like this, and I guess, hopefully I'm remembering it right. And this should be the response that will resemble what's our problem now? What am I doing wrong here? Comma. What's the problem here? Okay. Am I not able to call 2 times square root 2? What is that? It's not double. Maybe it's a symbol toolbox thing. No. Yeah. Interesting. What happens if I don't have double? It works. Okay. I might have added some parentheses that are not necessary. Seems like that. Okay. Then the step function. Oh, come on. What the hell? Put 3 and then plot this. Something with the figure. Oh no, that's not right at all. What about this? Nope. I remember that 2 times 0.707 was my thing here. Divide by 2, I'm not sure. Something like this, you would remember this. And I guess this was the right thing. But square root of 2 divided by 2 is not the value I was looking for. But, whatever. 2 times theta. No. Again, whatever. If you use if you use the Ziegler-Nichols method, you will most probably end up with a step that looks like this. It has certain overshoot and it has a certain settling time, which is most of the time not ideal and not suiting your needs, but it is a solution that is provided without effort, and it is a solution that is supposed to be a starting point for controller tuning. So Ziegler-Nichols doesn't actually provide you with a solution that should be used, but they claim that this method can be used for any system with a black box approach. So you don't have to know the model of the system. You just go ahead and try to bring the system to oscillation, and then you note 2 values about that. One is the gain that you've used to bring it to oscillation, and the other one is the oscillation frequency, and you use the time constant of that frequency, and then you can just come up with PID parameters. And the Ziegler-Nichols tuning method is, as I've said, it's quite a lot. It is a starting point for other tuning methods or for general control design. It is a starting point, since you can see that no one in the right mind would want a system that looks like this, unless it is a special application. I would assume. But if you have a car, if you have, let's say, a temperature control system, a liquid control system, it doesn't look ideal. It shouldn't overshoot, or it should have a special overshoot that has some reason behind it. By the way, the Ziegler-Nichols method is also not meant for linear systems, because there are too many tools to design for linear systems. What we are teaching it, we are also preparing questions about it. But the actual usage of the Ziegler-Nichols method is for nonlinear systems. So basically a starting point for nonlinear systems, and then you try to tune to get better solutions for the PID controller. So, and I have hopefully explained it here in my notes, so that you can use any methods. I've shown you here a analytical method that gives you the critical gain and the time period here, the time constant. So you can use a p-type controller, you can use that, and you can just go ahead and plug in j omega, which corresponds to the j omega axis. Since it should satisfy the j omega pair, plus j omega or negative j omega, you can plug it in and look for the solution, and you will end up with a complex equation. So the real part should be equal to 0 and the imaginary part should be equal to 0. If you equate the imaginary part to 0, you will get certain omega values, and using these omega values you can go ahead and calculate the k value. Once you have k and omega, it is very handy, since the solution will be sine of omega t and the frequency doesn't change with k, so you can go ahead and calculate the time constant. And you need k and t, and the formulas are given as follows: 0.6k, kp divided by the half of the time constant, and kp divided by the 0.125 times t. So basically this will give you a controller that has that looks like this, and as I've mentioned before, it will have a high overshoot and an interesting setting time here, but you might not want to use this, but you have to know how to tune using that. The phase controller looks like this, and the problem, the controller, the resulting closed loop, the root locus, corresponding root locus, and the step response, and the same for the tabulation method. So you can go ahead and examine this PDF and try to write your own code, or maybe try to manipulate the code that is given to you. But I highly recommend you that you listen to this lecture very well. Go back if you didn't understand anything, and then you can also use Google Classroom to ask me what if you have not understood something about the lecture or something about the control design process, whatever. I highly recommend you that you focus on this PID design. Go ahead and try to design a P controller, PI controller, PD controller, PID controller, or even I and D controllers, and look at the advantages and disadvantages. Most probably some homeworks will come about this, or you might have already an assigned homework about that. So since our course is called a control system design, this is basically constituting the first part of the three parts that we will be covering. This is the most important topic in the time domain, since it is the essentials of controller design, and PID type controller design is very important. If you think about it, as far as I remember, in the academic paper somewhere was written that most of the time, or in the industry, 98% of the controllers are PID controllers, and 90% of the PID controllers are PI controllers. Something like that. The numbers might be wrong or not up to date, but that's really the case. So most of the time, this structure is preferred over almost all other controller types because it is predictable, and being predictable is very important if you have safety if you are trying to have safety, if you are trying to have cheap implementation, etc., etc. So it has some advantages. Also, it has some disadvantages. These industrial applications are general applications, and if you are trying to have a high precision control problem, if you're trying to design a high precision closed loop, then you might want to look for some different control methods. There are plenty control methods, but it is essential for a control engineer to know the PID design process, because it is very important, and it tells you very much about systems and behaviors and the change in behaviors. And the trade-offs that are coming from the real-world applications are very important in this lecture. Okay, well, hope this video was helpful, and see you in the next lecture. Have a nice day.